In our previous video, we had discussed the means in which our heart cells are able to generate and propagate those action potentials, which are critical for initiating that muscular contraction, which allows our heart to beat. But what I want to do now is talk more about the conduction system in looking at sort of the main ways in which it propagates those action potentials. Now, we discussed two different action potentials in our previous video. We looked at the action potential of our cardiomyocytes, and then we looked at the action potentials of our pacemaker cells. Now, the pacemaker cells are critical because they're the ones that are generating that signal to be sent through to the entire heart. Now, when we're looking at the main structures of our conduction system of the heart, these are our pacemaker cells, starting off with the big one, the main one, and that is our sinoatrial node, our SA node. Now, this SA node is located in the right atrium, and what's going to happen is that it's going to undergo rhythmical spontaneous depolarization. Wow, lots and lots of syllables. Let's discuss that. Let's go into that. What does that mean? And this is something I implore you all to do throughout your studies. Rhythmical, okay? Rhythmical means rhythmic. It's in a rhythm. Spontaneous. Spontaneous does not mean the word you think it means. A lot of people think spontaneous means, rapid or on the spot or almost impulsive. In the world of science, spontaneous means something different. Spontaneous means it's able to do that thing by itself. So when we are looking at a spontaneous depolarization, what that means is that these pacemaker cells, in this instance our sinoatrial node, is able to depolarize without stimulus or without help from something else. So the same thing could not be said for our cardiomyocytes because it needed to reach that threshold. It needed a previous action potential to activate it. So we then have our AV node. Now our atrioventricular node is located in the interatrial septum, so on the left-hand side of the right atria. And what is going to happen there is that it's essentially going to receive a signal from the depolarized cardiomyocytes and then send the signal down into the AV bundle. Now, the AV bundle can also be called the bundle of His. They are both referring to the same thing. It just depends on the age and the region of the world that the source you're reading has been published. Most textbooks and most resources here in Australia refer to it as AV bundle, but just be aware it can also be referred to as bundle of His. I do not mind which term you use, just be consistent. Now, from our AV bundle, it's then going to move down and branch at the apex of the heart, so the very bottom of the heart, into our Purkinje fibers. Now, these can be a little bit tricky until we look at it in a sort of diagram like this. So, we have our SA node. This is our primary pacemaker. And what that is going to do is that's going to, as we saw in our previous video, leak those sodium ions until it triggers an action potential. That action potential will then be shared across all of these cardiomyocytes in the right and the left atria. It's going to be both atria, and that's really important because both atria are going to constrict at the same time. As I discussed in the previous series, what is happening is that both atria will constrict and then both ventricles will constrict. But again, we're going to be talking about that more in a moment. From our SA node, it's going to then move through both of our atria until it hits our AV node. Now, what is going to happen here is the AV node is going to have a delay. It's going to grab that signal and essentially just pause for 200 milliseconds, so 0.2 seconds. This does not seem like a lot of time, but in the world of action potentials and chemistry, that is a very long time. After waiting that 0.2 seconds, it is then going to send that signal from the AV node down into the AV bundle, again, also known as the bundle of His. And as we are moving down into our interventricular septum, it is going to split, okay? It's going to split into our right and left AV bundle, until we reach the apex of the heart. Now, once we reach the apex, it will then loop up the left and right side of those ventricles through our Purkinje fibers. So from the Purkinje fibers, those action potentials are then sent through to the cardiomyocytes in the ventricle, and that causes our ventricle to constrict. So SA node, AV node. AV node goes to bundle of His goes to Purkinje fibers, and Purkinje fibers wraps right up and around our ventricles. Now, something that's very interesting about this system is two main things. One, we have our action potential moving from our sinoatrial node across our right and left atria. Now, I've also said to you guys that our heart and all of our cardiomyocytes exist as a functional syncytium, so they function as one. So why is it that the action potential doesn't just go from our sinoatrial node and just through the entire heart? Why does it not move through when it needs this special AV node to pass through? And even then, that AV node has to delay. What is going on here? The big thing here is that if we have a look at this cross section of the heart, we can see with our valves, so these are our AV valves and these are our semilunar valves, they are surrounded by this fibrous skeleton. And what that does is it essentially stops the action potential from the atria jumping to the ventricle. And this is incredibly important because if we think about it, we want blood to flow nicely through the heart. We want it to go from the atria down into the ventricle and then from the ventricles out, out to the body. So this is incredibly important that the heart beats in a specific order. The atria constricts first, pushing blood into the ventricle. Then the ventricles constrict. This is why we have a delay at the AV node. This is why our AV node over here has a delay of 0.2 seconds. Because what is happening there is that the signal, the action potential is being sent from our SA node. That is spreading across our right and left atria, which is triggering them to constrict. Now, once our action potential hits the AV node, it pauses for 200 milliseconds or 0.2 seconds to allow the blood to move from the atria to the ventricle. Because if all four chambers of the heart, if both atria and both ventricle constrict at the same time, the blood won't go anywhere, it'll just gridlock. So it will have that delay to allow blood to go from the atria down into the ventricle. So from there, the signal will then move from our AV node down through our AV bundle, then to our right and left AV bundle. But it's sort of going right down to the very bottom of the heart, then looping back up. Why is that? The ventricle's right here. The ventricle's right here. Why doesn't it not just jump over? How I want you to visualize this is like a tube of toothpaste. If you're holding a tube of toothpaste and you want to get all the toothpaste out, you don't squeeze from the top and sort of squeeze down to the bottom of the toothpaste because the nozzle's at the top. If you're squeezing it down to the bottom, you can't push the toothpaste out. That's what we're seeing here. The openings for the ventricles for the blood to escape are here. So this is our aortic semilunar valve. And then behind that, we can see our pulmonary trunk. They're both up higher. So we want the heart to start constricting from the bottom and squeezing up to the top. We want it to start from the bottom, squeeze up to the top, because that's the direction we want to push that blood. We want to push it up and out. This is why with our heart conduction system here, our AV node and our AV bundle especially, our AV bundle goes right down to the apex, to the bottom of the heart, then loops up, connecting to our Purkinje fibers, and our Purkinje fibers then signal the heart from the bottom to the top to squeeze and push that blood out. Now, something I would highly implore everyone do is take this info that we're learning from this series and really incorporate it into what we did in the last series, because they all intertwine together. So we've seen this lovely diagram a million times before. Right and left side, we can see our great vessels and our valves. Now, what is also very important is that in amongst all of that information, we now start to introduce this electrical conductivity. So like our SA node would be up here, our AV node would be down here, Our AV bundle is in our interventricular septum, branching up into our Purkinje fibers up here.